Okay, everyone, welcome. For those who don't know me, I am Baris, Aksanli. I am a professor in the Electrical and Computer Engineering Department of San Diego State University. And today is the third workshop in our robotic workshop series. The IEEE student chapter at SDSU and HKN at UCSD have been jointly organizing these workshop series. And today our topic is going to be optimization. So we all know the word optimization and we use it pretty much anywhere, but without knowing the details of how to do it much. But if you are an engineer, regardless of what you do, your job actually is going to be about doing optimization one way or another. Either you do coding, either you do resource management, either you do logistics, well, whatever you do. And today what we are going to do is we are going to try to show you how to do optimization, or at least how to start formulating simple optimization problems and how to solve them in daily tools we use. And we are going to provide examples on two platforms to provide you flexibility. So these platforms are MATLAB and Microsoft Excel. They're both useful to solve optimization problems, and you'll see how powerful they can be. And if you have both of them, great, because we are going to show you how to create and solve these problems on these platforms step by step. So we're not just going to give you the code and try running it. We are going to build it together. If you don't have any of those, which is fine, you can access the recordings later and try to go over those steps one by one. And during the workshop, if you have any questions, please use the chat box. We are going to monitor it regularly and try to answer your questions real time. And with that, I'm going to leave the stage to my research assistant, Onat Gungar, who is going to show you the steps of these optimization problem setups one by one. Onat, it's your time.
Thank you, Dr. Aksanli. So let me share my screen first. Okay. Can everybody see my screen? I think there's no problem, right?
Yeah, it's good.
Okay, thank you. So, hello everyone. I'm Onat. I'm a second-year PhD student at EC, Electrical and Computer Engineering Department. Today, we are going to discover the world of mathematical optimization, where I will start with some preliminary information to understand what is mathematical optimization. Then we will focus on some sub-problems of mathematical optimization, and we will solve some problems. So you will have a chance to implement what you have learned during this tutorial. So let's start. So let's first define mathematical optimization. To define mathematical optimization, we first focus on optimization part. So optimization comes from the same root as optimal, which means best. So when we try to optimize something, we are basically trying to making it best, okay? So, all right. So best can change from context to context. For instance, if you're a basketball player, you want to maximize your shooting percentage and minimize your turnover ratio. You can do these at the same time as well. So there are different fields that we can utilize mathematical optimization, which is a branch of applied mathematics. So manufacturing is the most common one. So we have, for instance, transportation, scheduling, finance, and marketing. So there are also many more fields that we can count. So mathematical optimization, you can come across with the term mathematical programming. So programming here refers to planning activities. So mathematical optimization basically tries to find the best choice among a set of options. So we have set of options subject to a set of constraints or limitations. So when we try to formulate this in words to put the simplest you can think of, so where we try to minimize our objective, we have an objective function. By varying variables, you can also call this decision variables, subject to some constraints. So our objective function is the output we are trying to minimize or maximize. variables or decision variables that are the inputs that we can control and influence system performance, meaning that changing these values will eventually change the objective function. We also have our constraints. These constraints can be equality or inequality that limit the variable values. So to provide some examples, so far we have seen three components of a mathematical optimization problem, which are the essential components of an optimization problem: objective, decision variables, and constraints. So what are some real life examples for that? So portfolio optimization. So in portfolio optimization, we have a budget, we have a total amount of money, and the goal is to distribute that money among different assets. So the objective can be a minimization of the total risk or maximization of the total profit. The variables are nothing but the amount of money we should allocate to each asset. And with respect to, we have, of course, total amount of budget available, which is basically our constraint. So in transportation problem, for instance, our objective is to minimize the total transportation costs. With respect to variables, what are the decision variables? There are specific routes. We need to decide which routes we should use to transport goods between warehouses and outlets, for instance. One example for constraint may be related to inventory, total inventory amount we should hold. So in model fitting, machine learning. So machine learning is a field that we can continuously use mathematical optimization. In fact, we can model any machine learning problem using mathematical optimization. So model fitting means that we need to fit a distribution to a past data. So for that, our objective is to minimize test data error, for instance, or training data. The variables, parameters of the model. So let's take an example of neural network. So in neural network, we need to decide on how many hidden layers we need, right? Or how many neurons we should select for each hidden layer. So these are the variables, these are the parameters we should decide. So constraint is apparent, the model complexity limits us. So let's now formulate mathematical optimization, what we have learned so far. We call this standard form, meaning that we can convert any mathematical optimization into that standard form. So here we have our objective function, minimization, f0x, we call this our objective function, with respect to our constraints. So the first constraint is an inequality constraint, and the second one is equality constraint. So let's delve into the details. So x is nothing but an n-dimensional vector coming from a real field. This is the decision variable. So this means that basically we have a column vector which has n elements. Okay, so this we call this x. And f0, our objective function, maps from Rn to R, and this is our objective function, as I mentioned. So fi are the inequality constraint functions, similar to objective function. This maps from Rn to R, and hi is similar to that. We have this equality constraint function. So feasible set, knowing the feasible set is a real asset in an optimization problem. So we call this a set D a feasible set if we can satisfy the constraints. So given x from Rn, again, n-dimensional field, if we can satisfy the constraint, meaning that fix is less than or equal to 0, I from 1 to m, and hix is equal to 0 from I from 1 to p, if we have this set, if we can find solutions that can satisfy a constraint, that these solutions belong to our feasible set. So you can come across problem feasibility problem. This is nothing but trying to find the solutions that belong to feasible set. So here, note that feasibility problem is not it's not guaranteed to yield an optimal solution. This is just a feasible solution, but one of the solutions from our feasible set will be eventually our optimal solution. So we can categorize mathematical optimization problems under two categories: convex optimization versus non-convex. Before going into the details of convex optimization, I would like to talk about the terminology you should be aware of. So convex optimization terminology, we will start with the convex set. So we call a set C convex if the line segment between any 2 points in C is contained in C. So let's see an example. So here let's call this set C. So here let's take any 2 points, X and Y, all right? And we already demonstrated this on this figure. And we will select a constant, which we call as alpha, which is coming from 0 and 1 interval. And when we combine these points with the line segment, this should be within the convex set. So if this condition satisfies for every point in this convex set, then we call this set a convex. Okay. So I would like to ask you a question. So do you think this set is convex or not? Can we find any line segment which is outside of the convex set? Can you write it in the chat box so that I can see? Do you think this set is convex, the set C? Okay, any suggestion? All right, then I continue if you do not have any suggestion. Oh, I can, yeah, I have. Let me open. Yes, that's pretty good. Okay, perfect. Thanks for the answers. Yes, this set is, sorry about that. This set is convex, right? Because we cannot find a line segment which is outside of this set. So what about this set? Actually, I provided a hint, which is non-convex, right? Okay. So basically, we could find any 2 points and we connect these 2 points, which creates our line segment. A part of this line segment is outside of our set. So we call this set non-convex. Note that we do not call this set concave. So this is a common mistake. So this is not a concave non-convex set, okay? All right. We also need to define convex function. So we call a function g convex if we satisfy 2 constraints, okay? So the first one, domain of the function is convex. So what is the domain of the function? Domain of the function is a set where our function is defined. So for instance, what is the domain of logarithm x? It's nothing but 0 to, oh, sorry, plus infinity, right? So this is the domain of the logarithm x. Okay, this is the first condition. So what's the second condition? It is kind of similar to convex set condition, but this time we make sure that the line segment connecting any 2 points should above the graph. So let's see an example. So this is an example of a convex function. So take 2 points, again, x and y, okay? And let's connect these points on the function, of course. This is our function g, okay? Let's connect this with the line segment. As you can see, this line is above the graph, right? So we call this convex function. What about the other example? So let's call this g bar so that we can differentiate convexity from the concavity. So this time when we connect these with a line segment, this is below the graph. So we call this time concave function as opposed to non-convex set, okay? So this is kind of preliminary, you need to know. So let's delve into the convex optimization. So as I mentioned, we differentiate now optimization problems under convexity or non-convexity. So previously it was between linearity and non-linearity, okay? So let's consider again our standard formulation, as you remember. So we had our objective, our constraints. So here, in order to have a convex optimization problem, our objective should be a convex function. Okay, this is the first condition. Okay, the f0 should be a convex function. Also, we need our inequality constraint function to be convex and our equality constraint to be affine. So affine can be quite confusing term, but it is not. So it is basically a linear component plus some offset, okay? So we have some offset and we have linear part. So we call this, if we have 2 components, then we call this an affine function. So overall, we can write this formulation in more compact form. So we basically minimize the convex objective function f0 over a convex set C. So in order to write this, we write this as follows. So we minimize again f0x, subject to x is coming from a convex set C. So this is the simplest formulation you can come across when you're looking for convex optimization, okay? So there are different types of convex optimization problems. So we will focus today on linear programming, where we have linear or affine objective and constraints, okay? You can see quadratic programming. So in quadratic programming, as opposed to linear programming, we have convex quadratic objective function, but our constraints are still affine. You can come across second order con programming, semi-definite programming, or con programming. I will not go into detail of these problems. So let's start with the linear program. Let me first check the chat box whether we have any question. Why is that set not concave? Why is that set not concave? Go back. Okay. Oh, why is that set not? This is just a terminology. So we do not tell set is concave. Yes, you're right, Mark. Concave set that in terms of terminology, yes. Okay. So do you have any questions? Let me see. Is there a reason why concave is used for functions but not sets? As far as I know, there is not. So, okay. So okay, you're welcome. So let's continue with the linear programming. So linear programming is developed during World War II to plan expenditures and returns in order to reduce cost to the army. So it is developed for world to limit the expenditures of an army. So this is a historical fact. So in order to have a linear program, we again have different conditions. So the first condition tells us that decision variables should be continuous, okay? We have a continuous decision variables. This means that decision variable can take any value, okay? We do not limit the values that decision variables can take. As I mentioned, the objective function is linear and each constraint is a linear inequality or equality. Okay, so let's see LP linear program in standard form. So this may seem cumbersome, but do not feel. So again, here we have n-dimensional vector space here. So x coming from Rn. Okay, we have these constant vectors. So here we will write this in more compact form. Okay, let's see this compact form. So here we basically convert this vector notation into matrix notation. Okay, for instance, we have here m by n matrix. So we write this in AX, and on the right-hand side, we have a vector where we just write this. And similarly, we modify the objective function. So going from this step to this step needs proof. I will not go into detail of the proof, okay? So one important point is to show that we need non-negativity constraint on the decision variables. Okay, so how do we solve LP? So the simplest approach is called as the graphical solution approach. So this is applicable if and only if you have two decision variables. So this is really simplistic case, this is not completely realistic. Yeah, you have two decision variables only, okay? So the idea is based on the fundamental theorem of linear program, okay? Where you need to search only the corner points of the feasible region. So let's look at example. So here, let's first examine what kind of problem is that? So as we can see, we have an objective function, which is linear, right? So we have two decision variables, x and y. Okay, so we match the first criteria, right? So we have linear objective function, that's okay. And our constraints are also linear, and we also have non-negativity constraint. Perfect. So this problem is nothing but an LP, right? Okay. So now we try to solve this problem using graphical solution approach. So how do we solve this? So since we have two decision variables, we basically graphically solve this in two-dimensional graph. Okay. So here is the solution approach for that. So for instance, let's start with y less than or equal to 4. So we first draw the y is equal to 4 line. This is nothing but this line, right? Similarly, we also draw the remaining lines. In order to find the feasible region, what should we do? So if y should be less than or equal to 4, then we need to span the area below this graph, right? Similarly, if x plus 3y is greater than or equal to 6, we need to span the upper side of the graph, right? So when we take the intersection, let me clear that area. When we take the intersection, we end up with our feasible region, okay? This is nothing but this region already shown in this graph. So let's remember our solution approach. We now need to search the corner points. So what are the corner points? They are indicated here. A, we have A, B, and C, okay? So how do we find the points corresponding to these corner points? So A is nothing but a point where x is equal to 1 and y is equal to 4. So how should we solve this? We basically plug these points into our objective function, all right? Oh, I should pick another color. We should plug these values into our objective function, and we select the one which gives us the minimum solution. So note that our objective is minimization. So we do that. So x is equal to 1, y is equal to 4, z is equal to z. You can come across with z. Z indicates the value of the objective function, okay? So B, we do the same. And we come up with the final solution, which tells us the optimal solution is at point B, since it gave us the smallest number, smallest objective value, which we call as our optimal value. You can come across with those terms as well. And our optimal solution, x is equal to 1.38 and y is equal to 1.54. Okay, so how did we find this solution? Can somebody tell me? How did we find these x and y values? So this is the point B. How do we find the values of the point B? So as you can see, we have two lines intersecting. So when we solve this simultaneously, meaning that if we write them and like this, and if we solve this simultaneously, we end up with these values, okay? Okay. So the more general, the well-known algorithm is the simplex algorithm to solve an LP. So George Danzig developed this algorithm for efficient solution procedure for LP. So this is basically the most widely used, and you can find this algorithm hidden in many solvers to solve LP. So this basically based on the idea that we need to jump from one extreme point to another, and we stop until we do not further develop the objective value. Okay. So I would like also talk about the solver. What is solver? So solver, it is a software package. So that includes one or more algorithms. So far we have seen two algorithms, right? We have seen graphical solution approach, we have seen simplex. So software package that includes one or more algorithms to find solutions to one or more classes of problems. So far we have seen LP, for instance. So if you have these conditions, then it's basically a solver. So we have Groby, Mosaic, Cplex, Excel solver. So we will use Excel solver to solve LP. Okay. Do you have any questions so far? So I will I will now continue with the problems. So before that, I make sure that whether you have questions, let me check the chat box. Yes, again, Mark, this is based on the fundamental theorem of linear programming. So basically, you can obtain the solution. We can see this extreme point perspective in graphical solution approach. So this comes from the jumping from corner point, or you can come across with extreme point, comes from the fundamental theorem of LP. So I can provide you a reference if you're interested in. So I don't want to go into details since this is not the purpose of this tutorial. Okay. Okay, perfect. So let's start our examples. So the first example comes from the manufacturing. So let's read the problem statement together. So here we imagine you're an operations manager of a factory. So our goal is to decide on a production plan for the next week. Okay. So our factory produce 3 types of products. We call them as P, Q, and R, right? Using four types of machines, A, B, C, and D. So we assume that each of the 4 machines performs a unique process. So there is one type of one machine of each type. So each machine is available for 2,400 minutes per week. So we only consider per week analysis, okay? And we also assume that storage from one week to the next is not permitted, meaning that we do not deal with the inventory related issues, okay? This is another level of complexity. So we kind of simplified it. So we have operating expenses associated with the plant. So you can think this as a fixed cost, which is $6,000 per week. But this does not include the material cost, all right? So our goal is to determine the production quantity of each product to maximize the total profit given the available resources. All right, this is the simplest problem you can see for linear program, I think. So although it may not sound really simple at the first glance, but okay. So I have a simple question. So what components have we seen so far of a mathematical optimization problem? We had 3 components. Can somebody tell me what are these 3 components so that we can determine what are those components for this problem? Yeah. Can somebody help me? All right. What's the first component? Let me see the chat box. Yes, Mark. Yes, okay. Yes. So let's start with our decision variables. Mark, you're so fast. Maybe wait for other persons to answer a little bit. No problem. Okay. All right. The first one is decision variables. So can somebody tell me, other than Mark, let's say, what are the decision variables for this problem? Actually, I gave you plenty of hints, so maybe you can find. So I would like to focus on this part. What are the changing? Let me. Yes, that's better. Yeah, PQR is correct, but let's make this more concrete. So what are these? These are nothing but the production quantities we need to determine, like for weekly production. All right, what is the objective function? So this is already given. So what is that? What is the objective function, our second component? Yes, yes, Daniel, thank you. Maximize the total profit, right? So this is the objective. So what are the constraints? So we have one constraint here. What is that? So we are given that each machine is available for 2400 minutes per week, right? So this is the first constraint. We are given a table where we have another constraint. So let me go to that table. So here we are given two tables. So each table basically shows us the unit processing time. This means that, so for instance, for the product P, in order to process product P at machine A, we need 20 minutes. In order to process product Q at machine C, we need 6 minutes. All right. We also know that, what we know is that each machine is available only for 2400 minutes, right? So we can write, for instance, come here, 2400, 2400, 2400. So this table creates our first constraint, okay? We have also second table, which is related to product. So our goal, what was our objective, is to maximize profit. So how can we calculate the profit? So here we are given revenue per unit, material cost per unit, right? So how can we calculate the profit then? Per unit is nothing but, can somebody help me? Revenue minus material cost, right? So the profit is nothing but $45 for product P. Yes, that is correct, Kentaro. Yes. But we just look at the per unit. So 60 and 50, okay? We also, an additional constraint, which basically tells us we have a maximum amount of sales that we can make. Maximum allowable sales, 100, 40, and 60. This will be our second constraint. Okay, constraint. Let's continue with the problem formulation. So how can we formulate the given problem? Let's see that. Step one. I really like to divide the formulation into steps so that you can understand better. So step one, define the decision variables. We already know what the decision variables are. So determine the production quantity of each product. So let's call them small p, q, and r, which corresponds to how many units we should produce for each week, okay? Choose an objective function. So our company wants to maximize the total profit. So how did we calculate that? 45, remember we calculated in previous table. Revenue per unit. This is 60, revenue per unit if we produce Q, and so on. So what is that? Do you remember? So this is our fixed cost. But luckily, if we have a constant in our objective function, we can eliminate that constant since it will not change the objective value or optimal solution, all right? So we can basically get rid of that. So maximizing some constant will be again a constant. So this doesn't make sense. We can get rid of that, okay? So identify the constraints, this third and last step. So remember from our previous table, what do we have? We have machine availability. This is for machine A, machine B, machine C, machine D. Where do this constant come from? From the previous table. Okay, this constant come from previous table. Maximum allowable sales constraint. P should be less than or equal to 100, and so on and so forth. Please do not forget to add non-negativity constraint, where we need to make sure that each decision variable should take non-negative values. So to sum up, let me clear that area again. So our objective function is to maximization of our profit, right? We try to maximize our profit, subject to these constraints related to what? Related to what? Related to what? Okay, this one, right? We also write these in compact form. So this one is This part is related to non-negativity. This part is related to maximum allowable sales constraint. Okay, now it's time to go to the Excel so that we can model this. All right, I'm stop sharing my iPad screen and go to my Mac screen. Okay. Can you see my screen? Not. Okay, perfect. All right. So, sorry, sorry about that. Okay, let's open a new sheet. So, let me first confirm confirm that you all have solvers. Is there any problem with adding the solver, Excel solver in your Excel sheets? If so, we can go over the. Is there somebody that did not install Excel solver? Does everyone have solver? If yes, then I will continue with the. Okay, I don't see any problem. Okay, then. Now you will see whether you installed correct or not. I think it's a trivial. It's just a one step procedure. So, okay, I will separate my screen into two. All right. So the first thing I'm going to do, and as a general practical approach, you can also do that. So the first thing, okay, I will transfer my input, means that these tables, to my Excel sheet. So you can do together with me so that it will be a good practice for you as well. So machine. So we have products P, Q, and R. I'm basically transferring this table to here, A, B, C, and D. All right. So this table is nothing but unit processing time. So 20, 10, 10. All right. 12, 28, 16. Okay. 15, 6, 16, 10, 15, and 0. Okay, this is our first table. And also, let's write the availability. So we know that from our previous problem statement, each machine is available for 2,400 minutes per week. So let's also write that down. These are all equal. Okay, what is our second table? This is related to profit and maximum allowable sales, okay? So we know that, let's copy these, P, Q, and R. Let's directly write the profit. All right, what is that? 45, 60, and 50, okay? And we have also maximum allowable sales, which is our second constraint, 60, okay. So that's it for the input tables, okay? Now, we will start writing our decision variables. Let's start with the decision variables since I defined as the first step, decision variables. What are the decision variables? We already know that, right? Let's call this P, Q, and R. So these cells will be our decision variables. Let me make, yes. Objective function. Change this. So to write objective shortly, we will use sum product. So sum product basically multiplies two arrays and a sum them, okay, as its name called. So sum product. So this is our decision variable, and we will multiply this sum product with the profit. Okay. So this is our objective function. So now we will write our constraints. Okay. So the first constraint, again, we will use sum product. Okay. This one with the this row of the. So we are basically writing the machine A related constraint, right? So this should be less than or equal to, what is this? Availability value is 2400. So I strongly suggest to use formulation. So if I, for instance, come here and change this to, I don't know, something else, then it will automatically update it. So your machine can be updated, so availability can be updated, need to be updated. So let me change back this to, okay. So what is the second constraint? Again, sum products. Again, this one with the, this time machine availability B. I could use some tricks, but I want to do this manually. So this one. What else? I have also one constraint related to the machine D. Okay. Copying this. Okay. So this belongs to machine B, this belongs to machine C, and so on. Okay, what else do we have? We have also maximal availability constraint. So this will be P, this will be Q, this will be R. These all should be less than or equal to whatever the corresponding value is. This is 100, this is 40, this is 60. Okay. So we will make sure that the variables are non-negative using the solver. So far, do you have any questions? So now we are going to use the solver. Okay, if not, then let's click to Data tab, then click Solver, and you should see screen like that, interface like that, okay? Solver parameters. So the first one is the set objective. So which cell should I select? So this one, right? So 2, maximization or minimization, which one should I select? So we are trying to maximize our total profit, so it should be maximization. By changing variable cells, so we need to select our decision variables, okay? These 3 cells. Now we will add our constraints one by one. So when I click that, I should select the cell reference. And as you can see, we have different types of inequalities. So we will here select less than or equal to, and constraint add, and select the right-hand side value, add, left-hand side value. We already did these, so, and the right-hand side value. Okay, add, I think we have now 2, add, and the last one. Okay, let's click OK. So now we make our decision variables non-negative by selecting this box. So if you unselect it, then there's no guarantee. Okay, we should select this. So then we need to select the solving methodology. Okay, so we have nonlinear, simplex LP. Which one do you think is our target? Which one should we select? Can somebody write it? Yes, perfect. Thanks, Daniel. Simplex LP. So the reason I explained you the solution methods is that to see that picture. Now you know how I can solve an LP, right? using simplex algorithm. Let's solve it. Okay. So let's keep solver solution. So we can have also different reports. So we can have sensitivity analysis. This means that we can see the objective value changes or constraint variable changes, constraint function changes when we change the decision variable. So this is kind of post analysis after you solve an optimization problem, all right? So you can look at these analyses as well, but I would like to focus on the solution. So as we can see, these are the optimal solutions. So we found P as 81.8, Q as 16.3 or 4, R as 60. So our objective value is this. So this is the optimal solution, all right? So to make sure that whether we found the right solution, optimal solution, as we can see, that's the optimal solution is here. Okay, so I would like to take questions now. Okay, do you have any questions? So I cannot see the chat box. Okay. Were everyone able to solve the problem with me, or you just watched? Doesn't matter. Okay. So I'm continuing with the next problem then. Okay. All right. So this seems rather simpler problem. Okay. So if you're an Office fan, the Office fan, maybe you will be happy with this problem. So Dunder Mifflin Paper Company. So we require as a boss of this company, we require different number of full-time employees on different days of the week. So, but we need to make sure that each full-time employee must work 5 consecutive days and then receive 2 days off. So, for instance, an employee will work on weekdays and will 2 days off on weekends. Okay. So the goal is to formulate a linear program to minimize the number of full-time employees. Okay, so we are given this table. This basically tells us how many employees we require for each day of the week. So for instance, for Monday, we need 17 employees. For Tuesday, we need 13 employees, and so on and so forth. All right, so again, I would like to ask you the objective function. What is the objective function here? Can somebody help me? Actually, again, I gave you a hint. So the objective is to what? I cannot see the chat. Is to minimize the number of full-time employees. So each employee is costly, right? So we need to minimize that number. So this is our objective, okay? What are the decision variables? This will be kind of tricky. So let's see. Okay, I cannot control. Oh my God. Yes. So decision variable, decide how many employees we must hire. So let's call this yi, and this corresponds to the number of employees who work on day I from 1 to 7. Okay. Do you think by this decision variable we can solve this problem? What do you think? I want to hear some opinions. Do you think I actually gave it? Yes. Let me see. Okay, so this is actually not the right decision variable. So when we define this decision variable, we cannot put a constraint on the fact that each employee should work 5 consecutive days. So instead, we define the decision variable in this manner. So number of employees whose 5 consecutive days of work begin on day I. So this means that the employee start working on day I will also work on I plus 1 through I plus 4. Okay, so let me then continue with the integer programming. If we have time, then we will continue with this example. Okay, so I also want to show the integer programming part. So okay, sorry for the inconvenience. So far we have seen convex optimization, right? So we have seen one specific example in your program. Now we focus on non-convex optimization. So for convex optimization, we know that we need that our objective function to be convex and our constraints to be convex functions. So for non-convex optimization, we have a problem where the objective of any of the constraints are non-convex. So non-convex problems are inherently very difficult to solve. They're at least NP hard, there are saddle points. So for instance, neural network is a really great example for a non-convex problem, which is coming from machine learning. As I mentioned, you can model any machine learning problem, in fact. So we will focus on integer programming, but know that there are different kinds of problems, such as linear fractional programming, geometric programming, and so on. Integer programming. So as you remember, in our previous LP example, in fact, in manufacturing example, we assumed that our decision variables can take continuous values, right? So for instance, number of units to be produced during a week can take continuous values. So this assumption may not be realistic, as you might think. So we need these variables to take integer values. So we basically have three types of integer programming models, let's say. So pure integer programming, if we need to restrict all decision variables to take integer values, and we call this pure integer programming. In mixed integer programming, for some variables, we can restrict these variables to take continuous values, but for some, we need to restrict them to be an integer value. And we can also have binary integer programming, which tells us that integer variables are restricted to 0 or 1 binary values, all right? So IP solution approaches, enumeration is the simplest you can think of. So this means that we basically enumerate all possible solutions and then choose the best one. So this sounds really funny. So this is valid for only very small size problems. So if you have larger problems, so let's consider an IP model, in fact, binary integer programming model with 100 binary variables. Then we have this many possible solutions. It's not possible to work out with a traditional computer, right? Or in GPU, or I don't know. So it should take millions of years. So a very well-known solution approach is branch and bound. So this is based, again, it's like similar to simplex in terms of smartness. So systematic enumeration of all candidate solution, but we get rid of, we discard fruitless candidates, meaning that the solutions that can no longer develop our objective function en masse by using some lower and upper bounds, okay? So you can also come across implicit enumeration, cutting plane algorithm, and Lagrangian relaxation as some of the solution approaches. So do you have any questions before I will go into the example? Okay, so diet problem. So this is, again, like I first want to start with the simplest example you can come across. So this is the simplest example you can come across by searching through the MIP. So again, let's read the problem statement. Okay, so after a never-ending quarantine period, you realize that you gained 10 pounds, which is quite likely. So you immediately decided to make a better diet plan. So this is kind of different diet. So you are only allowed to consume 3 types of products: apples, oranges, and milk. All right. But we have a restriction. So we need to consume apples and oranges in integer quantities, whereas there's no restriction on milk. Okay. So there is a cost associated with each unit of product. Apple costs $1.5, orange costs $2, and each gallon of milk costs $3. All right. There is a restriction. Each day we must ingest at least 500 calories, 6 grams of protein, and 10 grams of sugar. So these will be calculated based on the provided table here. Right? This table is simple to understand. So it basically tells us if we consume one unit of apple, then we should take 70 calories. So if we consume one orange, then we get 3 sugars. All right, 3 grams of sugar. Sorry. We have also one more constraint, which tells us the number of apples consumed should be greater than the half of the number of oranges consumed. So I would like to show this. So I would like to show how do we write this constraint in. Let me switch back to my iPad. Okay. So what are the decision variables? The amount of product that we should consume, right? So x1 corresponds to the number of apples to be consumed. X2 corresponds to the number of oranges to be consumed. X3 is the gallons of milk to be consumed. Remember that these should be integer and this can take continuous values, okay? So the constraint, the first constraint is related to what? Minimization of the total cost. So where this constant come from our previous table. Okay, not the table, but the problem statement here. The first constraint, calorie constraint. So we must at least take 500 calories. So these are simple, but when we say at least, we should understand this inequality, right? At most, we should understand this inequality. So when we say at least we should consume that amount, then the left-hand side should be greater than or equal to whatever the constant on the right-hand side. So protein constraint, again, these are all related to table. What about, not this one, table. This is amount constraint. So this is kind of different. So I would like to focus on that part. So what does the statement tell us? So number of apples consumed, x1, right? Let's call this x1 since we already defined, should be greater than the half of the number of oranges, 0.5 x2 should be greater than. I write it wrong way. So should be greater than x1 should be greater than 0. So in optimization problem, we generally do not use greater than, less than, since this makes the feasible set an open set. Okay, you do not need to know these details, but just you know that this leads to an open set, meaning that we cannot find an optimal solution. Okay, so we want this to be inequality. So we need to convert this into inequality. So let's write this in that format. This should be greater than. So we just add some small number. Let's call this epsilon, okay? So that we have, let's call this 0.1, so that we obtain inequality. This is kind of smart trick you need to be aware of. All right, so we also know how do we write our amount constraint. And please do not forget again the non-negativity. Okay, and we now have integrality constraint, which means that x1 and x2 should take integer values. All right, so now it's time to, let me stop sharing, and sorry for the, I need to switch back and forth between the, okay. Now it's time to open your MATLab, so let me open mine as well. So now we use YAML. Did everyone install YAML? I didn't suggest to install solver since there may be many errors related to that. So let me share my screen. Okay, let me clean this area. Just 1 second. Okay. Solution. Okay. Now, let me share my screen. Okay. So, mixed integer programming example, direct problem. So we first define our decision variables. So in YAML, so YAML is a tool that you can model optimization problems, but you need solvers to solve. I think with YAML there are some default solvers coming with YAML when you install them. So you might be able to solve the problem, but it's not the point. So the point is how to model the problem using YAML tool. So this is basically MATLAB syntax so that you can easily model a problem using traditional MATLAB syntax, let's say. So define decision variables. This is the first step I taught you, right? So let's define. So in order to define decision variables in YAML, you have 3 options. So let's write them. So SDP var is the most general. So this is basically continuous decision variable definition, all right? We have int var. This basically means that integer variable. So we have also bin var. So this is binary decision variable definition, right? Okay. So let's define our decision variables. What is the first one? X1. This is number of apples to be consumed. So which keyword I should use here? Can I have an answer real quick? Yes. Somebody listening to me? Which is the keyword I just told you? Yes, thank you so much. Int var. So when I write int var, I should provide the size of decision variable. Now our decision variable is just scalar, means that I should put 1. But if you have, and if you are going to work in this field, you will eventually have like matrix inputs such as 10 by 20. Okay, but now we will consider the simplest case, all right? So x2 similarly will be integer variable 1. What about x3, which will be different? What's that? Is dp var 1. All right. So good so far. Now define our objective function. So we just basically transfer what we see on the right-hand side to the left-hand side of the screen, okay? So let's assign a variable objective, which is equal to 1.5 times x1 plus 2 times x2 plus 3 times x3, all right? This is done. We write our objective function. Constraints. So in order to define constraint, we first initialize our decision, initialize our array, constraint array. Okay. Constraints. Let's define this as an array, and we will concatenate to that array. So constraints is equal to. So in order to concatenate in MATLAB, constraints, comma, 70, we just write the first constraint, right? 70 times x1 plus 90 times x2 plus 400 times x3, which will be greater than or equal to what? 500. So we will do the we will complete the rest of the constraints. So I won't do that. You can do on your own. I will have all of the solutions, so you should also have. To solve the problem, let's say we completed our constraints. To solve the solution, solve the problem, sorry, we will use the optimize keyword, and we provide our constraints and our what? Our objective. So this will provide us solution. Let's call this solution. So if I have a question at this point. So if we only have provided constraints, which kind of optimization problem would it be? So I explained you previously. Can somebody tell me? So this is kind of, so it starts with F. So if this will be what? Feasibility problem, right? But now we want to deal with our objective value. So we will write back. Okay. So if we do not have any problem with the optimization process, then we should get solve the problem, which is an instance of a solution, will be 0. Then we can extract and display our values. So in order to extract the decision variable, we will use value keyword, all right? So when we write value x1, this basically tells us the solution of how many apples should we consume. So number of apples, let's say. Okay, so let me write the solution in fully. So let me open up this one. So as you can see, I completed the constraints: calorie, protein, sugar, amount, and non-negativity. Okay, note that I write this constraint in more compact form. Actually, you can write this constraint in one line, but I wanted to show this in separate lines so that you can be aware of the fact that we have many constraints, okay? So as you can see, we extract and display a value, and let's run this. So as I mentioned, so in order to solve this, you should either have, you should have definitely solver installed. This is not a difficult process. Since I think you're all students, so you can have an academic license. So for instance, I installed Groby solver here to solve the mixed integer programming. So you can also do the same so that you can have a solution. So I will give you as an homework so that you can play with different optimization problems, and maybe you will love it. Okay, let's run just to see the solution. Okay. So as you can see, it was pretty quick. So we can see the solutions, right? Solution apples is 2. We should consume 2 apples, 1 oranges, 1.2 gallons of milk, which leads to 8.6 as an objective value, which is the cost we are trying to minimize. One detail, let me check. We have still time. We have 20 minutes. Okay, perfect. One detail, in YAML, the default objective function is minimization. So as you can see, we write this in minimization form. But if we have a maximization, then we should write the negative of this objective value. Okay, I will have an example on that. So we can solve another integer programming example. I think that's more fun. So do you have any questions so far related to that previous example? Did you all follow, understand? Can somebody tell me something? I feel like nobody's listening. All right. Thank you so much. Okay. Okay. Thank you for your feedback. So let's look at the second example. So this is binary integer programming. So what was the binary integer programming? So let me ask you a question. Can somebody help me? Well, I don't remember what was that. So binary integer programming, BIP, what was that? Binary integer programming. So we need to make sure that all decision variables are what? Binary, can take 0 or 1, okay? So, yes, thank you. So this is coming from the serious community, so I kind of adapted the questions to be more fun. I don't know whether you like it or not. So CEO of Halfborn Wives, Piers Halfborn, decided to make an investment in order to use his father's $24,000 heritage. So he has 4 investment opportunities shown in the table. So he can invest in Shirley's Sandwiches, Greendale Community College, Senior Cheng Security School, and Abed's new movie. So he should invest certain amount, which will bring some value, right? So required amount is on the left, and present value, which means that how much money he will obtain is shown on the right. So we also have additional restrictions. So he can only make 2 investments. If he invests in Greendale, he also must invest in Abed's movie. If he invests in Shirley's Sandwiches, he cannot invest in Cheng's school. So the question, into which investments should Pierce place the money to maximize the total present value? This time I will not ask what are the decision variables and etc. So let's see. Decision variables. I call this xi, which is binary variable 0 or 1, indicating investment I is made or not. So for instance, if x1 is 1, then it means that investment is made in Shirley's Sandwiches. If it's 0, then do not invest. All right? So we have 4 decision variables, which are all binary. So the objective, maximization of what? Total present value. So this is given here. Maximize the total present value. Here is given. So 13 times x1, 11 times x2, 10 times x3, 5 times x4, and let's sum them up. Total heritage constraints. So Pierce has $24,000 he inherited from his father. So we need to put a constraint on the total amount of investment he should make, okay? So we have total number of investment constraints. Where does it come from? So he can only make 2 investments, means that the sum of the decision variables should be equal to 2, okay? The first dependency constraint, x2 minus x4, should be less than or equal to 0. Where does this come from? If he invests in Greendale, he also must invest in Abed's movie. This comes from here. If you're not understanding it really well, I can explain this later. So I want to show this in MATLAB again. Second dependency constraint, again, our second dependency constraint, I can explain later. So we also make sure that we have binary variable constraints, which was previously what? Integrality constraint, means that our decision variables was integers, right? So this time we have binary variable constraints. So let's model this in MATLAB. So where is my MATLAB? Great. Okay. Again, I provided some blanks to fill in. So define variables. What are the variables? X1. Well, what should I write on the right-hand side? What keyword? Can somebody help me? I forgot. Yes, I am expecting an answer. No answer? What was that? Binary variable. So I write binary variable, binvar. So this is again scalar, right? So we may have matrix or vector instead of 1. So we need to increase the size in that case. So since all our decision variables are binary, I will just copy this x2, x3, x4. Okay. So now we define objective function. So this is already given. Let's call this objective. And we do the same procedure that we did previously for the previous example though. 10 times, sorry, 10 times x3 plus 5 times x4. All right. So again, we need to write the constraints. What should we do first? We need to define the constraints as an empty array first, right? Then we fill this constraint by concatenating. Okay, so 9, I will again write the first constraint, then you should be able to do the rest. So 7 times x2 plus 7 times x3 plus, what's the last one? 3 times x4. This should be what? Less than or equal to 24. Okay. So this is quite similar actually. So let's look at the solution. So what was the X1? Surely sandwich is investment decision, whether we make an investment or not. X2, X3, X4. We write the constraints. Objective, this is kind of different. And you can either indicate the minus sign here, means that our objective is maximization, not minimization. Okay, so default value is minimization, default objective function value, minimization. So we need to modify this by putting minus sign in front of the objective function. Okay. Now we again use the optimize keyword, constraints and objective function. Okay. So if we do not have any problem, the solution, meaning that we do not face with any error while solving the optimization problem, then we need to extract and display the solution objective value. Okay, else we can trace back the error source. So let's again run on this. Let's see the solution. What was the solution? So the solution surely, meaning that peers should invest in Shirley's sandwiches and Abed's new movie. And objective value yields $18,000. All right. So do you have any questions? So we have 9 minutes. I can either go back to that problem really quickly. So if you can, if you want. So, okay. So do you have any question related to integer programming and how we solve it? Okay. If you do not have, then so as you remember, in our scheduling problem, our goal is to determine how many employees we should hire per each day. All right. So we mentioned that if we select this decision variable, number of employees who work on day I from 1 to 7, then this might not be the right solution, since we cannot satisfy the constraint that each employee should work 5 consecutive days. Instead, we will define another decision variable, which tells us number of employees whose 5 consecutive days of work begin on day I from 1 to 7. So if we have X1, then it means that the number of employees beginning to work on Monday. Okay, then we are happy with our decision variable selection. So step 2, choosing an objective function. So the goal is to minimize the number of hired employees. So we call xi the number of employees whose 5 consecutive days work on day I. So the goal is to minimize the summation of xi I from 1 to 7. So constraints, what are the constraints? So we have a number of employees required for each day. So for instance, for Monday, we know that X1 will start, we will work on Monday. X4 will also, the workers who will work on Monday. So we write in this manner, these constraints are written in that manner. So we write this for each day, and we also need to add non-negativity of the decision variables, okay? So we just write this, we just summarize the mathematical optimization problem on the right. Okay. We can also solve this since we still have time in Excel. Actually, I can directly show you the solution. So, and I can go over that solution. So scheduling, okay. So here's again, the first step is to transfer the input data, okay. So we have this many required employees per each day. And decision variables, x1 through x7, an objective function. Note that these should be empty since I already solved, these are filled. And our constraints related to required number of employees related to this table. So let me also solve it again. So let's check. What is the objective? Objective is this cell, right? So the goal is to minimize the total employee cost. By changing variable cells are the decision variables that we need to select, okay? Then we add our constraints one by one, okay? Then we need to make sure that we did this selection, so we make sure that our decision variables are non-negative. So solving method, what's that? Simplex LP, since we are solving a linear program. Solve it. Okay. I think that completes the tutorial. So I covered all the material I wanted to cover. So if you have any questions, I can take them. So thank you for coming and listening, paying attention. Could you explain how the conclusion part of the statement about convex works? Could you explain how the conclusion part of the statement? Can you elaborate on that question? What do you mean? Could you explain how the conclusion part of the statement about convex works? I didn't get that.
In the meantime, everyone can find the material used in this presentation in the GitHub page shared with the participants. So all the MATLAB code, all the Excel examples we made, and we are going to include the presentation file over there too. So if you were not able to follow the individual examples one by one, like here with us, you will be able to repeat those examples with by yourself later on if you choose so. And if you have any questions about the material presented today, feel free to email Onat or directly me. They would be happy to give you more resources as you need. Thanks a lot again to participate and stay here for an hour and a half. And now that we have only a few minutes left, I think we are going to be here until 5:30 to answer if you have any additional questions. But I think we are done, right, Onat? Do we have any additional information to show?
No, I'm done. I'm taking questions now.
Okay, so if you have any additional questions, feel free to put them in the chat box, and feel free to visit the GitHub page whenever you have the chance, and let us know if you have any additional questions.
Nice question. So how does the AX, oh, this is the definition of line segment. So if we select an alpha, a constant between 0 and 1, and if we write in this format, then this basically a line segment which connects X and Y. Does that answer your question? Okay, perfect. Thank you. Do we have another question? Can we review how simplex algorithm works? I can provide reference. Yes, you can search that. There are a lot of this is an iterative algorithm. You can actually search through a lot of examples. Yes. Daniel, does that answer your question? You can I think find a lot
I guess
of
he was
examples.
asking for individual step-by-step algorithm explanation, but I don't think we have enough time for that. What we can do is we can provide additional information about the simplex algorithm in our GitHub page. That would be the fastest given the time frame.
Yes, we can do that. Okay. I will take a look. You're welcome. Thanks.
Again, thank you everyone for coming at this time. The workshop series will continue next week. Professor Sean from UCSD will talk about machine learning next week. So if you want to attend that, make sure to follow the emails from both the SDSU IEEE chapter and UCSD HKN group. They will give you preliminary information about what the workshop requires to get yourself ready before the event. Thank you everyone again.
Thanks for coming.